Hi, my name's Fred Zell. I'm a geologist living in Pittsburgh, and for the last few years, I've been leading geology-themed hikes in Ohiopyle State Park. And I decided to create a YouTube video here and share it as a supplement to people hiking and enjoying the outdoors in this very popular state park. So let me get my screen going here. And this talk really started as a talk I gave at the campground in Ohiopyle in 2018, but there's been quite a bit added to it then as people have learned more about the geology of this area in recent years. And I'd like to especially thank Jim Shawless, who's newly retired from the Pennsylvania State Geologic Survey, for all his information and advice. He's learned a lot walking all these hills and valleys and mapping this area through the years. And also Frank Bizzaglia and his students at Lehigh University. You'll see a lot of their recent work here, which is really neat stuff. So here we go. Exploring the special geologic features of Ohiopyle State Park. There we go. Our objectives are for you at the end of the talk to see why the mountains and valleys here are so special, why it's such a special place. And what do the rocks and sediments here tell us about big picture Earth history? And you can see the agenda below that, original context, and then relationship between bedrock geology and landscapes, and then echoes of Earth history that are contained in the landscapes in Ohiopyle. And then there's a special topic that'll help you in looking at some of the rocks in Ohiopyle and understanding why they look the way they do, interpreting ancient traces of flowing water in sandstones there. Through the talk, I'll mention some other talks where you can go and learn a bit more, get deeper knowledge. This year with Pittsburgh nonprofit Venture Outdoors, I'm leading a geology-themed bike ride on each of the 25 major bike trails in Western Pennsylvania and adjacent states. You can see them in the circles here on the map. We've been on 20 of them so far. We have 5 still left. And to go along with those, I've lumped the bike trails into 6 themes of similar geology. And I've made a YouTube video for each of those. And 3 of those are especially relevant as background to some of the things that we'll talk about in this video about the Youghiogheny Gorge and Ohiopyle State Park. The glacial theme video has a lot of paleoclimate information in it. So if you want to get more background about climate charts that I'll show, that's a place that you can look. The rivers one, Allegheny and Ohio River valleys, focuses on how this whole river system was reorganized and deepened by erosion since glaciers started visiting Pennsylvania and this region about 2.5 million years ago. So if you want to learn more about why is there so much erosion on the Youghiogheny, why is it eroding so deeply and so quickly, why is the waterfall at Ohiopyle Falls eroding upstream, where's that erosion coming from, you'll get a lot more background about these major rivers and all their tributaries which are eroding down since glaciers came in and reshaped the river systems here. The other one that's especially relevant for this talk is the Laurel Highlands one, circled in green. And that one talks a lot about the bedrock geology, the shape of the land, ridges and valleys, and land use, different uses of land, how that relates to the soils and the bedrock geology. So there's a lot more about that in the Laurel Highlands talk. The other 3, the plateau talk, circled in black, there's a lot about energy resources throughout the plateau there, but including in the area circled in black. The one in orange, Conemaugh Uplands, has a lot of neat history in it. The Johnstown flood is included in that. There's a bit about the Portage Railroad that was part of the Pennsylvania Mainline Canal, as well as the Pennsylvania Railroad coming through there, the main line coming through there. And you'll get to learn what a hoodlebug is from the Hoodlebug Trail. That's part of that theme. And then the last one, the wilds, circled in medium green. Um, in that talk, you'll learn about what makes it wild in terms of including the geologic origin of why that's a wild place. So you can find these by going on YouTube and searching 22 and 22 geology, or just on Google. I think if you search 22 and 22 geology, you'll find them that way too. Or you can go on YouTube and just search my unusual name, Fred Zelt, and you'll be able to find these 22 and 22 videos, and then ones that are specific to topics that might be of interest to you. I warn you though, most of them are an hour long, so it's good to be able to relax when you watch them. So next topic here is the regional context. This is an elevation map, low in green, higher in red, and then white. You'll see a whole series of elevation maps like this. Hopefully you can see the outline of Pennsylvania here. You can see the area we're interested in. And I'm showing this over such a big area because I want you to see the context of where we'll be focusing in the bigger picture context. From the coastal plain here, from the edge of that to the lake shore or the edge of the lake here, this landscape was once buried, typically more than a mile deep, many miles deep in some places. All those overlying sediments and rocks have been eroded away. So it's a strongly erosional landscape, and the highs are held up by rock layers, rock units that are really resistant to erosion, the valleys less resistant to erosion. So it's like looking at the geology here, because all of this area once was in the subsurface, was deeply buried. And I want you to see that these are kind of on margin scale features, not just in this area where we'll focus in, but these features of the Appalachians, the Valley and Ridge province here, the high part of the plateau, the lower part of the plateau. Those are big continent scale features caused by a collision between part of northwestern Africa and this part of North America about 300 million years ago, give or take. So there was an ancient mountain belt raised up here that's worn down to its roots now, and it's the roots that we see at the surface. Zooming in a little bit, again, you can see the outline of Pennsylvania here. There's Maryland, here's West Virginia. Here's the area we'll be focusing on. And you can see some really intense folds of sedimentary rock layers with resistant to erosion sandstones holding up the ridges, limestones, which dissolve in rainwater, and shales full of clay, easily eroded, forming the valleys here. And these ridges are held up by especially quartz-rich sandstones. And you can see the shape of these. These are broad folds in front of this intensely deformed fold belt. And those broad folds continue up to the Youghiogheny frontier, and then there are really intense folds. You can also see that there are some river systems and streams that cut through the plateau here. This is the Youghiogheny River, Youghiogheny Gorge, cutting through Chestnut Ridge and Laurel Hill here. This is where Loyalhanna Creek cuts through. There's the Conemaugh River that cuts through both of those ridges. Here's Blacklick Creek cutting through. And this is the Cheat River cutting through Chestnut Ridge, this broad fold armored by resistant to erosion sandstones. And Cooper's Rock is right here on Chestnut Ridge, overlooking the gorge of Cheat River. And I'll just mention farther south than this map goes is the New River, which cuts across all this grain, all this Appalachian and plateau grain starting in North Carolina on the edge of the Blue Ridge. So the Yaugh cuts across this grain, but it's not the only river that's been able to cut through across this grain in this eroding landscape. Here's a geologic map and cross section that goes with it. The colors here indicate the ages of bedrock. These are sedimentary rock layers in the plateau here, from younger to older rock layers in this direction in general, although these are all hundreds of millions of years old, these bedrock layers. And in the cross section here, DD prime, you can see that in this low plateau area, the sedimentary rock layers are fairly flat lying. There's a fold, convex upward fold, the high part of the fold here of Chestnut Ridge. Here's the fold that's Laurel Hill. You can see at this scale, there's no squeezing of this cross section, one-to-one vertical and horizontal scales. They're large but pretty broad folds. You can see that there's another fold farther back here. And the colors indicate that there are older rocks exposed in the cores of those upward folds at the surface. And there's some younger rocks in the downward fold in between them. And it's some of these rocks exposed on the crests of these folds that armor them, made them resistant to erosion, and make these especially high areas. For example, Mount Davis, the highest point in Pennsylvania, is associated with one of these folds and a really quartz-rich sandstone in the Pottsville Formation that helps hold up that high spot. Here's another view of the topography. You can see these broad folds, Chestnut Ridge, Laurel Hill, anticline. There's a low fold or a concave upward bottom of a fold in between those that goes through Ligonier and the town of Ohiopyle. And there's the Youghiogheny River Gorge cutting across both of those. These are the other notches in them from rivers and streams that I mentioned before. Here's the one that's from the Cheat River. Here's another view of Chestnut Ridge and Laurel Hill, and then the downward fold in between that goes through Ohiopyle and Ligonier. And there's Youghiogheny Gorge cutting across those folds. This and other gorges in Pennsylvania were studied by some folks with the state. And here's a chart they put together showing maximum relief along the gorge indicated in the yellow bubble. And you can see that they've identified that Youghiogheny Gorge is the deepest gorge in Pennsylvania, a little bit deeper than it's very scenic Pine Creek Gorge in Pennsylvania's Grand Canyon in the north central part of the state. So the deepest gorge in the state, a very special spot, a very, very special place for a state park. And we're lucky to have public lands there. Now let's look at the folds and some natural fractures in bedrock in this area. Here's an elevation map again. There's Chestnut Ridge. Here's Laurel Hill. So these two upward folds or the high parts of folds, and then the low part of the fold is going through here, going through Ohiopyle, with those sandstones armoring the edges of these folds. But here you can see the river has cut through quite deeply in this fold and has eroded into some softer and older rock layers within the gorge here. The next illustration we'll see goes between Connellsville and toward Confluence. So it's a geologic cross section that goes across these folds, including through Ohiopyle. Here's this geologic cross section. The different age rock layers, sedimentary rock layers, are indicated by the different colors. One of the ones that's especially sandstone rich with quartz rich sandstones resistant to erosion is the Pottsville Formation. And in the upper part of that, in places the Homewood sandstone occurs, it's an especially quartz rich resistant to erosion sandstone. It forms the high point at Baughman Rock overlook. It forms this high point on Laurel Hill. This is where the Youghiogheny River has cut across this fold and has cut down into older, softer rock layers. The Homewood sandstone's also the sandstone that forms Ohiopyle Falls, also Cucumber Falls, as you'll see. And you can see that it's armoring Chestnut Ridge here also, these resistant sandstones of the Pottsville Formation. This cross section is 17 miles across, and this is elevation, so this is 600 feet. It's highly squeezed laterally. These are much broader folds than the way this appears. And again, you can see the top of this is the very irregular surface of the land. So it's a cross section of the earth. Okay, let's look at another feature of these folds, and these occur both on the upward part of the fold, like this illustration shows, and the lower part of the fold too, or the other downward part of the fold, the bottom of the folds. These are formed by compression, but in these hard, brittle rock layers, as they folded, they would fracture too. And some of the fractures are compressional fractures from the compression between the right and left. You can imagine compression here causing this fold. And those are the green ones here. But also there's extension. So as you bend this brittle layer, there's extension. And so those are some red fractures that can form with bending this brittle rock layer. And those are parallel to the direction of the folds. And you also get perpendicular fractures as well associated with this compression and folding. And we're going to focus on these red and blue orientations and look at those because you'll see some amazing things that are in the landscape that relate to those directions. So here are the folds again, Chestnut Ridge, Laurel Hill, other folds farther back. And you can see these two orientations parallel to the folds and across the folds that we saw in that schematic. Now we're going to look more closely at the trace of the Youghiogheny River at Ohiopyle and in the Youghiogheny Reservoir relative to those directions. So here are those directions again. And here you see the Youghiogheny River. There's the town of Ohiopyle. You can see these straight reaches of the river that are parallel to these fracture orientations, these regional fracture orientations. There's Youghiogheny Reservoir, there's the town of Confluence, and you can see the same thing here, really accentuated by the lake being here, but these straight reaches of the river along these fracture orientations. And when you go down and look at the rock in detail, you can find all of those fracture orientations that were shown on the schematic in this area. I've seen all of those in Ohiopyle State Park. And on the next slide, I'm going to show you a really good example of that from Entrance Rapid here on the Youghiogheny River. It's going to be a picture that's looking downriver, and you'll get to see the bedrock exposed. So here's the bedrock. It's sandstone in the Pottsville Formation at Entrance Rapid. We're looking downstream to the west-northwest. The mouth of Cucumber Run is down here. This is Entrance Rapid. And see these planar vertical surfaces on the edges of these rocks? Well, those are really well expressed natural fractures in one of those orientations that I showed. And as you saw from the map, and you can see from this, this fracture orientation seems to have localized this reach of the river as other fracture orientations localize some other reaches of the river. This is something that's been observed for a long time. This is not new for me. I mentioned here that there's a nice publication you can find online that details this as well. But it's a very clear feature of the details of the landscape here. And if you want to try to get your mind around how this happens, one thing to do might be look at waterfalls when you're there in low water, and you can see natural fractures in the hard bedrock there. And you'll see notches typically in the lip of the waterfall from these natural fractures. And those kind of guide the waterfall as it erodes upstream. So that's one way to think about and look at how these might, in practice, these zones of weakness might help form the reach of a river. Okay, now we'll look at some really special and scenic spots and talk a little bit about the geology there, a couple waterfalls, and then the Baughman Rock overlook. And to do this, we're going to zoom in the area inside the red box so you can see what part of the area we're going to be looking at. So there's the town of Ohiopyle, there's Ohiopyle Falls, Cucumber Run here, Cucumber Falls, And we'll also look at Baughman Rock overlook here. You can see the middle of the low part of the fold and the middle of the high part of the fold um, of the Laurel Hill anticline and the axis of this syncline. So these two are really pretty close to the axis of the syncline. And by the way, these are generalized traces from Jim Shollis's recent work. So there's Ohiopyle Falls, about 20 foot tall or so. There are a couple people seated on the rock over here for scale. And there are three things you need for a waterfall. One is erosion to be working its way upstream. And again, I suggest looking at the talk about the Youghiogheny and Upper Ohio rivers if you want a lot more detail about why there's a couple hundred feet of erosion working its way up these rivers and their tributaries. So there's erosion working its way upstream here. A layer that's really resistant to erosion, in this case, the Homewood sandstone, full of quartz, very hard rock unit, resistant to erosion. And you need a rock unit to form a plunge pool that's soft. And underneath this layer, Jim Shollis assures me there's some coal, and associated with coal often are underlying really weak shale layers. So there's some really weak rocks underneath this that form a plunge pool. It has all the ingredients for a nice waterfall. And I'll mention a bit later about rate of waterfall retreat upriver. The Niagara Falls, for example, is retreating upriver very rapidly. It has a huge volume of water going across it, and it's retreating at a rate that people have observed in a human lifetime. When I look at old photographs here that go back 130 years or so, these rocks are in the same place. I really don't see any difference in this waterfall. And I've done that kind of thing with Cucumber Falls and also Buttermilk Falls in Beaver County, which is held up by a quartz-rich sandstone, a lot like this, and similar in age, maybe not exactly the same age, but similar in age. And those all seem not to have moved, at least since the photographs were taken 130 years ago or so. So there's a little data point for you when we talk about timing of migration of waterfalls. The next waterfall we'll look at is Cucumber Falls here on Cucumber Run, right in the axis of the low part of the fold. It's held up by the Homewood sandstone, according to Jim. And there are some coals underneath and some really soft shales that are commonly underneath coals, really soft clays formed under peat swamps that became coals. So this has the ingredients of erosion working its way upstream, a really hard rock layer underlain by a really soft rock layer to make a plunge pool. And this is a great place to visit. You'll notice a person here for scale. It's a great place to visit in all seasons. You can see it's pretty amazing at times in winter too, when polar vortex comes to visit. Now we'll look at Baughman Rock. We're going to look at two pictures here. The first picture is just looking out into space here and toward the axis of the Laurel Hill anticline, and you'll see this ridge in the distance. So this is Homewood sandstone. It's the same sandstone that holds up the waterfall here. And here, the sandstone, instead of being flat like it is at both of these waterfalls, it's tilted down to the west northwest. I hope you can see that it's tilted down here to the west northwest. Picture a rock layer tilted down in that direction. And you'll see a picture of that. Well, the same rock layer comes back on the other side of this big fold here in the high part of Laurel Hill with the axis in between. And the river has eroded in the gorge here down into those older, softer rock units, including shales full of clay, sandstones that don't have as much quartz in them, and some limestones too that dissolve in rainwater. So a really resistant quartz-rich sandstone holding up these high points, and the same rock layer, according to Jim's work, that's holding up the waterfalls, more than 1,000 feet structurally lower in elevation. You might think of that cross section we saw earlier on. So here's the overlook, looking off to the east-northeast. There's that high part of Laurel Hill I mentioned. The same rock layer I'm standing on here at the overlook comes back there and holds up the high point. In fact, Turtlehead rock that we'll talk about later is up in that high area. And then in between, here's the trace of the Youghiogheny River, Youghiogheny Gorge cutting through here. And the rock layers, bedrock at the surface here is older bedrock, softer, more easily eroded than these sandstone layers that hold up the high points. So a great place, again, great to see in all seasons. This is the rock I was standing on at the overlook. It's this Homewood sandstone, quartz-rich sandstone, and the top of the sedimentary rock layer is here, and you can see that it's tilted down to the left. It's tilted down to the west-northwest, associated with that folding 300 or so million years ago that created the broad folds in this area. Okay, now let's look at how the rocks here and sediments fit into the bigger picture of Earth history. And to do that, we're going to look at some charts of Earth climate that go back 500 some million years. The talk about the glacial area of northwestern Pennsylvania in the 22 and 22 series describes the origin and basis of this and other related charts. It's from oxygen isotopes, proxy of temperature. And this is interpreted to represent global temperature going back in time from today, time zero, going back first thousands of years. These are 5,000 year increments, 200,000 year increments, million year increments, 10 million year increments, 100 million year increments, going back more than 500,000 years, based on oxygen isotopes in ice cores from Antarctica and Greenland, where there are the blue lines here. And then the black and other color lines come from marine fossils, from the fossil shells of things that lived in the seas, going back again 500 million years. This is degrees Fahrenheit. This is degrees C on the vertical axes. And again, you'll be able to learn more about the basis for this, among other places, in that 22 and 22 glacial talk. This is the last glacial maximum. This is when glaciers were coming down into Pennsylvania, covered Canada, much of northwestern Europe. And we're in an interglacial period now. There still are thick glaciers in Greenland and Antarctica, but they're not covering all of Canada like they were in the last glacial maximum. This last glacial maximum was 18 to 20,000 years ago. And since then, many of those glaciers, ones that covered Canada, for example, have melted, releasing water into the seas. Sea level's actually risen 120 meters. And there have been pretty significant climate changes, as you can imagine, with glaciers having been down in Pennsylvania at that time. And you can see the interpretation of several degrees C difference between this last glacial maximum and this interglacial period where we are today. We'll look at this part of the chart in some detail a little bit later. It's just good to notice from this that this interglacial period that we're in now, there have been others in the past. There have been other glacial periods too, many of them going back about 2.6 million years, alternations of interglacial periods with colder glacial periods. You might also notice that in this interpretation, the last time Earth generally was about this cold was about 300 million years ago. And there are rocks in Ohiopyle that are about that old and older. So this is a time period represented by rocks in Youghiogheny Gorge. And we'll take a quick look at that first, and then we'll come back to the younger ages and those glacial interglacial cycles. I should mention that there were glaciations, continental scale glaciations at this time too. So surely climate at sea level would have gone up and down quite a bit in detail at this time, but those details aren't shown on this more smooth chart. Where we are in Pennsylvania, though, at this time, 300 million years ago, was very close to the equator. So there weren't glaciers at Ohiopyle 300 million years ago, but the climate certainly had variations in it, and there were sea level changes too that were important. So here's a close-up of the older part of that chart, and the rocks in Youghiogheny Gorge are Devonian to Carboniferous in age. And you can see in this interpretation, there's a big change, a big variation in global climate during this period, which is many tens of millions of years. And in these samples from the visitor center at Ohiopyle State Park, you can see some Devonian red beds of this age. There was a seaway that came into this area and had a limestone deposited, the Laurel Highlands limestone, a marine limestone. There are coals and river deposits and floodplain deposits. Again, in this area, we were close to the equator, so there were peat swamps here, not continental scale glaciers. And so these rock types reflect really big differences in climate throughout this period, and are generally consistent with this interpretation of general changes in global climate. So those are recorded in the rocks in our area. Here's a quick look at interpretations from proxies of CO2 in the past. CO2 concentration, you can see, is on the vertical axis. Right now, it's around 415 parts per million. It's been much higher in the past when there were dinosaurs, for example, in the Triassic, Jurassic, and Cretaceous periods. Ferns growing at the pole, CO2 is thought to have been much higher. Earth was a lot hotter than today. But the last time CO2 was about this low was coming into the Carboniferous here, including ages of rocks that are in the Youghiogheny Gorge and Ohiopyle State Park. So it's an analogous time for time we're in, at least in part, in terms of some of the rocks that are exposed there. Okay, now let's look at that younger time slice. Remember, there were glacial-interglacial cycles, many of them in the last 2.6 million years. This is a map of glacial deposits in Pennsylvania, either deposited in front of or underneath glaciers, or water-washed deposits of glacial age in yellow. The dashed lines here in both northwestern Pennsylvania, where glaciers came in, northeastern Pennsylvania, where glaciers came in, those dashed lines represent the interpretation of the maximum extent of glaciers in the last 2.6 million years. So, and in yellow here, you can see some water-washed glacial age sediment that came down into river systems. Here where we are in Ohiopyle, we're far away from these thousands of feet thick continental scale glaciers. We're still in a high area though, and there could have been pretty thick ice and snow accumulations here, but not part of these continental scale glaciers that covered all of Canada at times in the last couple million years or so. This is the upper parking lot across the street from Youghiogheny Park, or Ohiopyle Park Visitor Center. And this is during the 2021 Field Conference of Pennsylvania Geologists. There's a guidebook for that conference available online. You can Google and find it. And there's a lot more detail about some of the things I'll talk about in technical articles in this guidebook. So here's a group of geologists listening to Frank Bizzaglia talk about his work and the work of his students here. And this is a river terrace right behind him. He's standing on sandstone bedrock that's in place. And on top of this is a sedimentary deposit. It was never buried thousands and thousands of feet deep like the bedrock was. Bedrock was buried probably 10,000 feet deep here for hundreds of millions of years. It got cemented into solid rock. Instead, on top of this are sediments that were laid down by an ancestral Youghiogheny River. There's soft sediment, clay, sand, silt here. It's yellow in color in this case. And you can see these rounded pebbles, cobbles, and small boulders that once rolled along the bottom of the ancestral Youghiogheny, more than 50 feet above the current level of the Youghiogheny. So this is an ancient river terrace well above the current level of the Youghiogheny River. And Frank and his students studied these and age dated some of them. And that's their work that I'll show in the next couple slides. So here's something that comes from an undergraduate thesis at Lehigh, as well as a guidebook article from that field conference last year. And in map and in cross section, you can see these terraces that they mapped, from older terraces up high to younger terraces down low, closer to the current river. The town of Ohiopyle is built on some of these terraces. On these river systems in general, flat river terraces perched above the current floodplain were great places to build towns and cities. And there are a lot of examples of those along the upper Ohio, Allegheny, Monongahela rivers and their tributaries. They also got some age dates here. You can see age dates they got for the terrace where he was standing are about 305 or 368 million years, or 1,000 years, give or take, tens of thousands of years. That's the uncertainty on those. They got some other age dates too. Those we might look at if we look at a cross section here of the surface and the terraces. So AA prime is this cross section going down the hill down to the current river level, Youghiogheny down here, and then going up on the Ferncliff Peninsula, going down the west side of the Ferncliff Peninsula. He identified more terraces there, and down to the level of the Youghiogheny on this side of the peninsula. And here you can see the age dates that they got, and they've used these and other age dates they've gotten to kind of extrapolate and interpolate using erosion rates for the river system here, what they think were likely ages of other terraces. But some of these are dated directly. So again, the older terraces up high, younger terraces down low, from 1.2 million years old to about 42,000 years old for this youngest, lowest terrace. And you can see that this is good evidence that this big bend in the Youghiogheny River has been cutting down through time in more or less the same spot, with the Ferncliff Peninsula having been preserved for at least the last million years or so. And the overall rate of downcutting of the river downstream of the waterfall, where the erosion rate is higher than it is upstream, but downstream of the waterfall, about 50 meters per million years, which is a pretty high rate of erosion as things go globally. You'll notice that there are some data points down here too on Cucumber Run. We're going to talk about those in a lot of detail in a little while. So here's the cross section again, this time easier to see, bigger and spread out a bit more. These various river terraces going down to the current river level. You can see the age dates here indicated by the stars. And this is a climate chart. It's based on oxygen isotopes from microfossils, marine microfossils. These are warm periods up on the top. This is our current interglacial period that's been the last 12,000 years. This is the last maximum of glaciation, last glacial maximum about 18 or 20,000 years ago. And you can see that these interglacial cycles and glacial cycles have alternated. The scale laterally on this is in thousands of years. So here's 200,000 years ago, 400,000 years ago. You can see that scale up there. And all the details of this global climate curve are named and numbered because they're used for identifying what part of this that you're in different parts of the world. And you can see these age dates that are dated directly, as well as the ones that are extrapolated and interpreted. They're all thought to be kind of this part of these glacial interglacial cycles, around the glacial maximum or the part of the cycle when you're heading down into the maximum. And you can imagine that climate today, with freeze-thaw cycles, snow melt, ice melt in springtime, climate may have been very different at other parts of these climate cycles. There could have been much more ice and snow accumulated in the highlands, even though we're not in a continental scale glacial area. At times, there could have been a lot more ice and snow a lot more ice and snow melt, profound freeze-thaw cycles, very different conditions, and potentially much larger amounts of water in the river systems with very powerful erosion at different parts of the climate cycle than in the last 11 or 12,000 years in the interglacial part that we're in now. And you can see that this interpretation is consistent with that part of the glacial-interglacial cycle having lots of sediment going through the system at that time associated with those terraces. The next part of this that we'll look at is the youngest part coming out of the last glacial maximum into the interglacial. And we're going to look at waterfall retreat rate. There's Ohiopyle Falls, the town of Ohiopyle. I wanted to show you this oblique view of the landscape with north going to the left, because this is a clear view of some of the features that we'll talk about when we look at maps that are oriented with north to the top, as is normal. So here's Ohiopyle Falls. It surely is migrating upstream through time and has migrated around this loop. As we saw, this river has been in the same place for a very long time. So surely this waterfall has been migrating around this loop. And when it came up to the mouth of Cucumber Run here, it would have split, and Cucumber Falls would have come up Cucumber Run, while Ohiopyle Falls continued to march up around the path of the Youghiogheny. And it would have passed the mouth of Meadow Run also. The water slides are right here. It's a cascade, not a waterfall. It doesn't have all the features a waterfall needs. It has erosion working its way upstream, and it's a cascade, but it doesn't have a really hard layer with a really soft layer underneath. It has a fairly hard sandstone layer that forms a cascade. So it has one of the ingredients of a waterfall, but not all three. So I just wanted you to see this perspective and get the idea of Ohiopyle Falls having migrated upstream through time, passing the mouth of Cucumber Run, mouth of Meadow Run, and here it is in its current position. I'll point out, we'll talk about Entrance Rapids. This is Entrance Rapids, just below the mouth of Meadow Run. You can see Cucumber Rapids, and you'll see some of these other very popular whitewater rapids going around the Ferncliff Peninsula. And these are age dates that we'll talk a lot about in the next couple slides that have come from the Lehigh University Research Group. Now, here's a view with north to the top as normal. It's a close-up now of the lower part of Cucumber Run. There's the road, the parking area, the waterfalls right about here. And the stars indicate places where the Utah or the Lehigh group got some age dates. This one, there we go. And you can see that ages in thousands of years, 17.9 plus or minus, and other age dates. And they make a pretty neat story. It was Christy Lee who worked on this as her senior thesis at Lehigh. I had a chance to talk with Christy in the field conference last year. And these data points make a pretty neat story of timing of exposure of bedrock getting younger with erosion in this direction. You can imagine the waterfall working its way up in this direction, except for this one. And this one I thought was kind of suspect, and I wondered if it wasn't a block of sandstone, because there are a lot of blocks of sandstone on the landscape laying around that aren't in place, and could have had an origin that's different than the uncovering of the bedrock and the other data points. And Christy, when I spoke with her, seemed to think that that was very reasonable. She remembered that they took a sample from a block of sandstone that wasn't in place. So if we discount that one data point as having a different origin and just look at these, it makes a pretty neat story for the migration of exposure of the bedrock and migration of the waterfall, splitting of the waterfall between Ohiopyle Falls and Cucumber Run between 18 and 15,000 years ago. If we look at this now, oh, and by the way, this data point, Christy confirmed, is from downstream of Cucumber Falls. if we look at those on this climate chart, this temperature chart that we saw earlier, and again, the time scale changes right here. These are 5,000 year increments. We'll focus on this. There's the last glacial maximum, 18 to 20,000 years ago, coming up into the current interglacial period. And you can see that these dates show a lot of movement of the waterfall and then not much movement at all. And again, I mentioned in the last 130 years, doesn't seem to have moved at all. The blocks of sandstone below it are still the same. The blocks, the sandstone on top has the same shape. So it looks like it moved a fair amount. And then during the last interglacial, doesn't seem to have moved hardly at all. And that's consistent with the idea of much more water in the system at other parts of the glacial interglacial cycle, and a lot more strength of erosion of the streams and rivers than in the current part of the climate cycle that we're in today. So this is a sort of a hypothesis then based on data. And I should point out, as Frank always points out, that this interpretation I'm conveying is describing these data as though they're bedrock exposure ages. You can also interpret the data in terms of erosion rate of the bedrocks, and that's an equally valid interpretation. So I'm kind of taking one way of interpreting these and weaving it into a story and a testable hypothesis. Okay, so here's the same chart with those ages, with their age date ranges. The three that we talked about here. These are my little schematics for waterfalls. There's Ohiopyle Falls today. There's Cucumber Falls today. Those are those dates of bedrock exposure, interpreted as when the waterfall passed those points. And obviously, since this point, Ohiopyle Falls has migrated quite a bit, and Cucumber Falls just a little bit. And as Frank and others have said, that's because there's much less water. It's a much smaller watershed for Cucumber Run than the much larger watershed. And by the way, draining lots of upland areas for the Youghiogheny River here. So the Youghiogheny River seems to have moved quite a lot faster than Cucumber Falls upstream. There's the Meadow Run, and I mentioned the natural water slides are a cascade here. And this is a testable hypothesis that most of the movement of the waterfalls was during this part of the climate cycle, not so much during this part of the climate cycle. One way to test that might be for someone to come and get the same types of age dates for bedrock exposure here too. If this hypothesis is correct, then that age date should be somewhere in this range, not in this range. This is sort of halfway around the curve here between this age date and today. And if it was a steady state erosion rate, it should be, an age date somewhere in here. But if it gives an age date somewhere in here, then that's consistent with the more rapid movement of the waterfall during this other part of the climate cycle. So a testable hypothesis and relating this to global climate. Okay, the next thing we'll look at is some neat stuff, again, from Lehigh University group, and Turtlehead Rock here, which is a high point on Laurel Hill. It's a little bit east of the axis of the fold here that's mapped by Jim, but still one of the highest points of Laurel Hill, held up by that quartz-rich Homewood sandstone. And there's Turtlehead Rock. You can see the Homewood sandstone here, and I think you can see why it's called Turtlehead Rock. It's really deeply weathered, especially for such a resistant to erosion sandstone. This looks more like a limestone that's easily dissolved in rainwater. But this is a very hard quartz-rich sandstone. It looks really unusual. These rock faces were age dated, and they're not that old. that they've been exposed. But this one is interpreted to have been exposed based on the data for something like 248,000 years. That's a long time for this rock to have been exposed. And you can see the way it appears in the weathering. Or another interpretation of the data would be a really slow erosion rate up at that level. So there's Turtlehead Rock. And now let's look at that in terms of what was happening with global climate at that time. If it really has been exposed for something like 248,000 years, look at the interglacial, glacial, interglacial, glacial, interglacial cycles. Look at all the all the climate events that would have happened while that rock was exposed. And it would have gone through literally millions of freeze-thaw cycles. So certainly a rock that's seen a lot, a pretty tough rock. And now you get to see what a really deeply and long weathered rock looks like. Okay, the last topic here is to help you interpret some of the things that you'll see in the Homewood sandstone and other Pottsville sandstones and some of the other rocks in the gorge in Ohiopyle Park. And to do this, I'm first going to show a snapshot from a YouTube video. I encourage you to watch if this doesn't make sense to you. It helps to see it in motion. But this is the side of a flume. It's like a trough, like an aquarium. This is a glass wall. There's sand here that's a couple of inches high. There's a current of water flowing on top of the sand. Sand grains bounce along the top. There's erosion on the top. And then there's turbulent flow here. The sand grains drop out, and the next ones drop out, the next ones drop out. And it forms this cross lamination that tells you that the flow of the water was from left to right. This turbulent flow also causes scour of the older sand layer that would be underneath this. So there's scour here, inclined deposits in this cross lamination, and a bit of scour on top too. And when you see this inclined lamination, you know which way the flow of water was. This kind of feature can be a sand dune in a desert that could be 100 feet high or more with these inclined laminations. You see rocks like that in national parks in the West, in Capitol Reef National Park, for example, in Zion, huge cross laminated sets from wind-blown sand dunes. It can be tens of feet high, inches high from sand dunes underwater. It can be a small fraction of an inch. So they can be all different scales by flowing air or water. And we'll look at some that formed in sandbars and rivers at Meadow Run Waterslide and then Meadow Run Cascades. And these would have been formed in sandstones that are over 300 million years old. So sandstones that were with rivers flowing from the mountain belt that was formed off to the east. First, we'll look at the Meadow Run Waterslide. Here's some more pictures from the Field Conference of Pennsylvania Geologists last year. And this is a stop that's described in the guidebook too, if you want more information about this. So this is the water slide. And the next picture you'll see is of this rock face. You can see a little bit of the steps leading up to the parking lot here for the water slides. You'll see that in the next picture as well. So here's the picture there, the steps. And I hope you can see the really good cross lamination in this unit. There's a top and a base to this sand layer. There would have been a little sand dune migrating at the bottom of a river here. And it shows you that the current here was flowing from right to left. Now that you're cued into that one, I hope you can see some others here, other indications of cross lamination, similar current directions. And those were all measured by the field conference leaders for this stop and are in the guidebook in the article about this stop. So some cross lamination at water slides. Now we'll look at a really neat cross lamination feature farther up Meadow Run at the Meadow Run Cascade. This is the lower part of the cascade, the upper part here. The next picture I'll show you is an overview of the upper part of the cascade, and then we're going to zero in on this part of the outcrop here. So this is the upper part of the cascade. The next pictures I show you, I was standing on this rock, taking pictures in this direction, looking at this rock feature. In particular, And you can see these rock layers in the picture too. So here I am standing on the rock, and I hope you can see the cross lamination in these rock layers. So here was a sand dune migrating along the bottom of a river. It shows that the flow here of water 300 some million years ago was from left to right. You can see the same thing in this layer. It's in the other layers too, a consistent flow direction. You can see the same thing here as well. This is actually a little preserved sand dune with a linear crest. So the cross lamination indicates the current that deposited this was flowing from left to right, just like these. This one has a sandstone layer capping it though. And so this little sand dune was preserved here. And on the lee side of it, the downstream side, this is actually a scour pit where that turbulent part of the flow would have scoured into the underlying rock layer here. This is actually another cross lamination set going in this direction, a different sand dune than this one, an older one that was cut into by the flow that came across the sand dune and was turbulent. So this is really cool. I really haven't seen another feature like this, at least so far in Western Pennsylvania, an exhumed sand dune over 300 million years old. There's a mason's hammer or a rock hammer for scale. The amplitude of this, the height of this ancient sand dune, it's about 1 meter high. So a pretty cool feature if you go up to Meadow Run Cascade up near the top. You saw this outcrop before. You know that this is the Homewood sandstone, and this is the top of the sandstone bed tilted down to the west, northwest. And now, with your eye clued into these cross laminations, I hope you can see the faint cross laminations in this sandstone outcrop too. And those laminations are going away from us. So this was deposited by a river that flowed away from us, and you can see the traces of that ancient sand dune on the face of this rock outcrop at Baughman Rock. So to summarize then, we've talked about the general shape of the land, how that's formed by the bedrock geology here, the valleys and ridges. We've also looked at some of the details of how bedrock shapes the reaches of streams here, caused by natural fractures in the bedrock and zones of weakness. We've looked at some big picture relationships between the rocks in the gorge and in Ohiopyle and changes in climate hundreds of millions of years ago. And we also looked at global climate relative to things like the river terraces as the Youghiogheny River cut down through time, and also the waterfall details of waterfall migration in the context of those glacial interglacial cycles and climate over the last million years or so. So those are the topics I'd hope to cover, and I hope this doesn't take the place of you going out and looking at rocks here on your own and exploring these and other great spots. This is not by any means all the really neat geology in Ohiopyle, but I didn't want to make this talk even longer. So I think that's enough for this. And I hope you get out there and enjoy Ohiopyle State Park. Take care.